So we are getting toward the end of the semester. I hope that the load is not too high. I guess you're going to have some finals ahead of you. Surviving tired. That's more worrisome. The rest are good. Okay, let's start. Okay. So we are going to have 4 speakers today, and let's just get to it. I think the first one is Re'i.
Yes, hi.
So why don't you go ahead and share your screen?
Sure. Can you all see my screen?
Yes.
Great. So I'll start in a few moments. So, hi everyone. Today we will be talking about an article published in Nature in May 2008. It actually has more than 40 different authors. It is called an extremely luminous X-ray outburst at the beginning of a supernova. But a different title to this presentation may be Why Astrophysics is So Cool. So, in this picture you can see the galaxy NGC 2770. I think it's beautiful, don't you?
Yes.
Yes, thank you. All right. So Professor Weiss told us at the beginning of the course that we should do a 20 minutes presentation about a good story in science. It could be a new discovery or an exciting revealing, or maybe it could be a finding a good fraud scientist and tell his story. So just for a few moments, I entertained myself with the idea. Who is the best fraud scientist that we all know? Anyone has any idea? We all know him. No, no ideas? He might be fictional. Of course, I'm talking about Professor Gilderoy Lockhart from Harry Potter 2. Anyone who knows Gilderoy Lockhart knows how fraud scientist he is and actually got people believe him just by his beautiful smile. But unfortunately, he does not have any Nature article published, so I couldn't choose him. All right. So let us begin with the question of what is a star. A star is an astronomical object comprising a luminous spheroid of plasma held together by its gravity. Stars can come in various sizes and masses. We usually measure it in relation to the mass of our sun, which we call solar mass. Just for an example, the smallest star is called OGLE, TR122b, and its mass is only 0.1 solar masses. The biggest star is called R136A1, and its mass equals to 265 solar masses. And the thing that characterizes stars the most is its nuclear activity. Most of the star's life, it will transform hydrogen into helium with nuclear fusion. This is the first and the main phase of any star's life. In the second phase, which only happens if the star's mass is big enough, it will transform helium into carbon. And the third and the last phase of a star, again, if he is big enough to do it, it will have a very complex nuclear activity that will create oxygen, magnesium, silicon, and eventually will create iron. The light that we see from the star is actually its nuclear activity. This is what makes the difference between a star and a planet. A star can create its own light using its nuclear activity, where a planet just reflects it. Okay, so now let's ask ourselves what holds a star together. We talked about its nuclear activity, and we talked about its gravity caused by its huge mass. Those forces actually create an equilibrium. It prevents the star from just collapsing or dissolve into space. So as you can see in this diagram, there's this core, pressure caused by its nuclear activity that's pushing the star outside, and its gravity that's pushing it inside. This process creates the equilibrium which holds the stars together. Okay, so we discussed so far about what is a star and what holds it together. Now let's ask ourselves a different question. What is the difference between astrophysics and astronomy? So, in the first picture, I can show you Galileo Galilei showing the Doge of Venus how to use a telescope. Galileo Galilei is maybe the most famous astronomer. But what does it mean? It means that most of his science work was mapping the universe. he tried to find new objects in the sky. He measured the stellar object movements. He actually discovered 4 new moons of Jupiter. They are called Io, Europe, Ganymede, and Callisto. But he didn't ask himself what was the physical or the chemical properties of those objects. And from the other side, there is William Herschel. As you can see, there is a prism here, causing the light to disperse. He dispersed the light of the sun, causing it to show its different colors and wavelengths. He was the first scientist to actually say the term invisible light, and he discovered it by mistake. He measured the temperature of the different colors. When he measured the temperature of the red spot, he thought it would be interesting to measure the temperature near it, where there is no light at all. To his surprise, the thermometer still showed a higher than the room temperature, even where he didn't saw any light at all. So that made him think that there is something he called invisible light, that there is more than light than just our eyes can see. This is what set the ground for astrophysics. This tool, that which we'll talk about later, is called spectroscopy. This is the main tool that helps us understand what is the star that we are looking at is made of. What are its main atoms in there? And we can say it just by looking on the way that the star's light is dispersed. So to summarize this slide, astronomy is mapping the sky. You can be an astronomer if you're holding a telescope in your rooftop, trying to find new objects in the sky. Whereas astrophysicists will try to understand what we are seeing. What are the physical and chemical properties of that object? What is it made of? There is more than light than just what we can see. Nowadays, we know way better than William Herschel did at that time. And here is a diagram that shows it, the electromagnetic spectrum. The visible light marked here in blue. It is just a small part of the spectrum. There is a lot of information hidden in different frequencies of the light. It can come in visible light, infrared, ultraviolet, X-ray, and every one of them has different properties. But they are all the same phenomenon, which we can simply call light. Once you get the light from the star in the universe, you can disperse its light and then understand what is it made of. I won't go really into it, but it is a very interesting subject in astrophysics. So we will now talk about what is a supernova. A supernova is a powerful and luminous stellar explosion. It happens in the end of the star's nuclear fuel. But what does it mean? As you can see here, the pressure that is pushing the star outside, resisting to the gravity that's pulling it inside. Now, when the pressure ceases to exist, there's nothing that holds the gravity from pulling it inside. The pressure stops because there is no more nuclear reactions that can happen inside the star. As we said before, there is a complex set of nuclear reactions inside the star, eventually ending up with iron. Once you go into iron, there can no longer be any nuclear fusion because this atom is very stable and thus not capable of doing almost any nuclear reaction. So at that exact moment, when there is not enough fuel there's nothing that holds the gravity from pushing the star inside. So in a matter of seconds, the core starts to collapse and its outer shell is exploded outside. This process creates a very powerful and luminous explosion that can be seen from light years away. This process includes a burst of X-ray emission, neutrino particles, and gravitational waves. The supernova is so powerful that it will continue to light for many years. And we can differentiate between different types of supernovae just by their spectroscopy. This process means the death of the star. The only thing that remains is a neutron star or even a black hole if its mass is big enough. Now let me ask you a question. Which star will die faster? Will it be the more massive one or the smaller one? What do you guys think? Give it a shot, guys.
The smaller one.
I know your name, John. I saw that you're also an astrophysicist. So yeah, obviously I was right. The answer, of course, is that the bigger one will die faster because it consumes more fuel per time, meaning it will die faster. So bigger ones die faster. All right. Now let's talk briefly about the life of a star. As you probably understood, the thing that matters the most that determines the life of the star is its mass. So in a very simplified manner, smaller stars that their mass is up to 8 solar masses will end their life as a planetary nebula and then a white dwarf. Heavier stars have more complex nuclear reactions and they will end their life as a supernova. If their initial mass is between 8 to 20 solar masses, they will end their life in a supernova and later becomes a neutron star. If their initial mass is higher than 20 solar masses, they will end their life in a supernova explosion and then leave a black hole. So, I told you how supernovas happen. So, what else is there to know? The general picture of core collapse supernova has been known for many years, but the exact details of the explosions remains unclear. And here's something that might surprise you. Most of supernova simulations fail to produce an explosion. So, can we really say that we know how supernovas work? The main problem is that until now, all supernovas were discovered in a few hours delay, meaning only after the explosion already happened. It's preventing us from observing the process of the explosion itself. The very first moments of the supernova called shock breakout, and it's characterized by a strong X-ray emission. Now, as a result, the progenitors, meaning the star that created that supernova, and the events leading up to the explosions remains unknown. My instructor always gives a good example. Imagine you are examining a car exploding, and you want to know what caused it. If you're investigating it, you would like to get the video of the explosion itself, or even a few moments before the explosion happens. You will have an extraordinary little knowledge about what happened just by looking at the burned car. So, what did they discover? They reported the early discovery of supernova 2008D. And here are two main quotes from the article. So the first one is, here we report the serendipitous discovery of the supernova at the time of explosion marked by an extremely luminous X-ray outburst. And the second quote is, we forecast that the future wide-field X-ray service will catch hundreds of supernovas each year in the act of explosion, and thereby enable crucial neutrino and gravitational wave detection that may ultimately unreveal the explosion mechanism. This is the first time, actually, that ever scientists observed supernova as it occurs. You can see this in this short video here, the actual X-ray burst captured by the Swift telescope. Okay, now we'll discuss about the transient they found. But first, what is a transient? A transient is a sudden and short in time emission of electromagnetic wave. In 2008, on January 9th, at that hour, they discovered an extremely bright X-ray transient during a scheduled Swift X-ray telescope mission, meaning they found this transient by accident. The telescope looked at that location as part of its usual missions. They caught it by coincidence. By the way, observation of that area just 2 days earlier revealed no pre-existing X-ray sources at that location, meaning it is actually a transient. The transient lasted about 400 seconds and was captured at one of the galaxy's spiral arm. As discussed earlier, this is the galaxy NGC 2770. Here you can see the NASA's Swift telescope, an X-ray telescope orbiting the Earth, who discovered that transient. Here you can see the X-ray emission that they caught. You can see the light curve.
Can I ask you a question? What is the transient? Is it a supernova? What is it really? I mean, in this case.
A transient is the first emission that supernovas have. All right?
Okay, thank you.
That's even before any light is detected, right? Just X-rays.
Yes.
Okay, thank you.
This is the first phase of the actual supernova before you can see it in optical light. The X-ray is preliminary to the explosion itself. So here you can see the X-ray emission that they caught. You can see the light curve of that emission versus time. This graph is first of its kind. No one ever caught the X-ray emission at the beginning of a supernova. Immediately after they understood,
What energies? I mean, did they just measure the specific width? Because it's not clear from the plot. Like,
this is the
what
X-ray
are the
count
energies?
Yeah, but I
countering-
guess they had a filter, right? That question is about, how many
Okay. I'm imagining they looked
mega
at
electron volts or kilo electron volts or whatever. What is it?
I
Okay.
don't actually, all right, I'll continue, I'll maybe answer it later.
Okay, no problem.
Sure. So immediately after they understood that the X-ray burst is interesting, they alerted several other sensors to look at that location in the sky. One of those sensors is the Gemini North Observation Telescope. It is a giant structure surrounding a huge telescope. The structure's height is about 21 meters, and the main mirror's diameter is about 8.1 meters. They were able to begin the measurements of the spectroscopy after 1.74 days after the initial outburst. No one was ever capable of capturing detailed spectroscopy of a supernova so close to its explosion. Here you can see the actual spectrometer results. The x-axis is the wavelength in angstroms, and the y-axis is the flux. Different lines represent the day of the measurements. Those lines actually representing the atoms that the star is made of. This kind of data allows scientists to better understand the explosion mechanism. All right, that was the story behind this article. Now I would like to discuss about what we are doing in our research group, guided by Dr. Maayan Sumaniek. We are trying to find those kind of transients in existing data. We mainly work with the Chandra Space Telescope. You can see it in the background of the slide. Chandra is a space telescope developed and launched by NASA, and it is an X-ray telescope surrounding the Earth. Finding new transients, even retrospectively, could lead to finding new supernovas. Nowadays, there are advanced sensors trying to capture neutrino emissions and gravitational waves. One of the things that we are trying to do is cross-correlate those kind of emissions with interesting findings from the X-ray telescope. Here in this picture, you can see our group. This picture was taken at the Israel Academy of Science and Humanities at a conference about joining Israel into the European Space Agency, the ESO. So, I hope this presentation convinced you that astrophysics is cool. Now, if you are not convinced yet, here is a little example that might convince you. Here in this picture, you can see the list of the Nobel Prizes in the last 6 years. I circled the years that the Nobel Prize was given for an astrophysical discovery. As you can see, in 3 out of the last 6 years, it was an astrophysicist who won the Nobel Prize. Nice, isn't it? John, I think we are in the right profession.
Yeah, I hope so.
So, and to finish the presentation, I would like to show you this picture of Andromeda Galaxy taken by the NASA's Spitzer IR telescope. One of the most interesting questions is there anyone out there in the Andromeda Galaxy looking at us in the Milky Way, trying to find new phenomena and understanding the universe just as we do? That's it, and thank you for your time.
Thank you so much.
Thank you.
Thank
Great.
you.
That's quite non-traditional to the course. You actually educated all of us in astrophysics, and thank you so much. I definitely found it very, very interesting because I know nothing about astrophysics. Any questions? The paper is now open for discussion. Any questions to E?
I'm trying to understand this story. I mean, it was interesting. The whole thing was interesting. I mean, you really taught us about astrophysics, but trying to like, what is the bottom line? I mean, is there a bottom line or just like an intro for?
They found.
Maybe let me just continue this question. Just in analogy to microscopy, you can do time-lapse microscopy, you can identify events, and then you can go backwards. Where you saw an event, you can go backwards and ask what you had before. So what is surprising to me is how come the first observation is only in 2008 or 9? I mean, people could have done long-term observations, see the light. I mean, you mentioned observing the X-ray, but I guess seeing supernova by light, visible light, is more common. I don't know what the frequency is. It would be interesting if you know what the frequency is. Then in principle, you should always be able to go back if you do, time-lapse astronomy.
What's interesting about this discovery is that they actually caught the first sign for a supernova. This is the X-ray outburst. Once you see it in a visible light, as common as done before, you are seeing it after it happened.
No, I understand.
Yeah.
What I'm saying is you could look at the skies, have both visible and X-ray detectors, just turn on your acquisition and acquire for a long time. Maybe some the galaxies that are suspected to maybe have supernova events. Then you see the events in light, which is a late event, but you know exactly where it is, and therefore you can go to your X-ray detector and look back.
Yes, but
so I'm just curious because I think it's a question of frequency. How often do we see that?
Can I ask something? I mean, sorry. Go ahead.
Go ahead.
I'll ask later.
Well, let's get an answer and then you'll ask the next question.
Sure. So as far as I know, if you're looking at a big at a large field of view, you won't be able you won't have the enough resolution to see where it's coming from exactly. So it's a matter of question about.
So it's a field of view,
the field of view versus resolution.
Okay.
Actually.
So you need to have enough photon counts basically to measure anything in the X-rays. So you're really looking for a needle in the haystack. That's the issue.
Yeah. What's best about the Swift telescope that discovered it is that it has a very large field of view X-ray sensor. So it was the first one to discover it.
Okay. Right. There was another question.
Yes, it's like a few parts in this question. First, I want to understand what is the difference in time between the let's call it pulse, the X-ray pulse and the visible pulse, and what is the differences? Few hours. Okay, and okay. So one thing is what is that time scale tells you? That's one thing. Another thing, if you compare the intensities both of the X-rays and the visible, can you learn something from that as well? I mean, just wondering. That's all. Thank you.
I'm not sure I'm capable of answering it.
You're looking at the photon counts in the X-ray versus photon counts in the visible. Is the ratio meaningful, or you expect some universal ratio between the two?
Actually, I think it's a good question, but I don't know how to answer it. No idea. And
it tells you about the expansion rate of the supernova. The time difference between when the optical photons can get out and when the X-ray photons can get out. That tells you how fast the supernova is expanding, and that can tell you something about the energy. I don't know in terms of the ratio of the optical flux to the X-ray flux. I'm not sure.
Yeah, and I guess also the what you've shown out, there is a rise time and a slow decay, and I guess the rise time is also very meaningful in terms of
the main tool is spectroscopy again, because it tells you what are the atoms that you're looking at. This is the main tool.
And once you have the 4 hours later visible light where you have specific atomic lines, I guess you again can correlate between the X-ray and the light.
Mm-hmm.
Any other questions? All right, thank you very much, Rui, again.
Thank you.
And our next speaker is Avi. Is Avi here?
Yeah, hold on 1 minute. I'll just share the screen. Okay. Okay. Hi, good evening. So I'm going to speak about another scandal. It's not that I'm so familiar with the scandal, or wasn't until I put this together. It's also not a field that any of my research comes into contact with. However, I thought it was sensational, and due to its link to England, which is where I come from, and the San Baurilan link, I thought it'd be interesting to have a look at it. So the sources I used were, one is For Better Science, which has been, it's a website that's run by someone called Leonard Schneider. He's a Ukrainian-German scientist whose field originally was molecular cell. He was a molecular cell biologist, but seems to spend now most of his time running this site, which basically just seems to cover fraud within and issues within the scientific world. The other one is PubPeer, which is another whistleblowing site to deal with scientific scandals. And they both together is where most of this information has come from. In fact, the person who initially did the whistleblowing and actually forced the institutions to look at this, someone called Claire Francis. Claire Francis is a pseudonym that appeared initially in 2010. Most of her critique is of scientific publications, anything from poor statistics to figures that seem to clash, to graphs that don't seem to fit. And she sent hundreds, or he sent hundreds of whistleblowing emails. The name Claire Francis, I'm assuming was chosen on purpose, is actually also the name of a famous novelist. It's assumed it's not the same person. They don't know who the identity or the occupation of this individual is, or it might be several individuals. I mean, it's something that I'd like to discuss afterwards. Is it fair that there are these floating pseudonyms that can take down a scientist who may either actively, willingly, or possibly just due to mistake, have put out papers that have issues in them? Now, the Baurilan connection, I'm assuming anyone who studies on campus recognizes this building. It's called the Wall Center. It was commissioned by the Maurice Wolf Foundation. It's a 38,000 square foot building, which seats, has an auditorium which can sit over 1,000 people. And it cost roughly 43 million shekel to be built. Now, the reason that's important is because the same Wolf Foundation, during the years 2013 to 2016, made a donation to a certain institution called the Birkbeck University in England for roughly over £5 million in sterling. That's over 20 million shekel. And that's going to come back later on to play a part, possibly a very substantial part in this story. So who are we talking about? The individual's called Professor David Lachmann, and he's a professor at both UCL and Birkbeck. If you look at the Guardian clippings here, they all look exactly the same, pretty much, apart from the adverts on the side, which are more recent. But you can see it's 2017, 2019, 2020. So it's not something that happened one day and just went away. But these articles seem to come up periodically. Now, they actually started in 2014, but England was too busy dealing with fallout of the World Cup. So they were busy with something else. But the first whistleblowing emails came up in 2014. Now, if we look at who this professor is, he's one of the, or was, and possibly still is, that's the issue. This is not an end, a story with an end to it. He's a professor of genetics at Birkbeck and UCL. He's actually the master of Birkbeck from 2003. He's now called the vice chancellor. So he's someone who's very, very high up in this institution. He was awarded CBE, which is an award by the Queen for all of his efforts in higher education. And he's he is or was one of the country's leading geneticists. He also happens to be paid more than any other leading geneticist in the country by Birkbeck University. Now, this university is the same university that was receiving these very high grants from Morris Wall Foundation. The person who, or the lead person who makes decisions with regards to those funds is this very same David Lachmann. He's the nephew of Morris Wall. It doesn't mean that everything he does is tainted, but that you should remember that when we now look through what's going to happen over the next few years. So the initial investigation into Professor Lachmann and his papers was between 2014 and 2015. 28 papers were investigated, or at least were cited for investigation. 8 of the Lachmann papers were set for retraction. Eventually, 2 were only retracted and 6 merely corrected. 6 more papers were screened, and errors that were deemed too minor, or at least that's what the statement came out, that they were too minor to justify any further investigation. Now, my math isn't great, but 8 plus 6 does not reach 28. So the question is, what happened to the other 14 papers? Well, UCL at the time, who was the main university involved, they claimed that UCL confirms that this conclusion of its investigation is that Professor Lachmann has no case to answer in relation to research misconduct. They found that there are some obviously other people involved, other people who were written on the papers. He didn't know about it, he couldn't have known about it, etc. Lachmann's lawyers claim that the other 14 papers that were analyzed were found to be baseless. Whereas someone on the inside, one of the investigators, who was also a professor at the university called Professor Hardy, said that there simply was no time to screen those 14 papers. So we've got at the moment different versions of exactly what's going on within this committee that was appointed. So at a later date, one of the websites that I mentioned above managed to get hold of John Hardy, or Professor John Hardy, who was actually made a Sir later on for his what he did for the world of science. He's an award-winning geneticist as well. He was a UCL professor of neurology, and he's also a fellow of the Royal Society, I think, of Neurology. So the next few slides are a bit overcrowded, and I apologize, but we're going to see some of the things he said. So when he said I was the chair of the first committee, because there were 2 committees, we're still looking at the one from 2014, 2016, investigating the allegations. When appointed, fully expected them to be baseless. So we thought everything was just going to be nothing. However, to my horror, and that of my fellow committee members, nearly all of the ones we could check were correct. Our report was very clear that Dr. Lachmann, as a senior author, should bear the weight of the responsibility, especially as there were no other authors common in the papers. So UCL tried to spread it around. Well, different people are responsible, but it doesn't make sense that everyone else is responsible on papers that weren't necessarily co-authored by the different people responsible. He also claimed that their response was watered down in response to objections from Dr. Lachmann's lawyers. So what they said and what the university actually put out wasn't necessarily in line. No direct evidence that Dr. Lachmann himself had ordered the fraudulent image manipulation endemic, so they weren't able to actually pin it to him. However, we were horrified that his current employer, Birkbeck University, put out a press release saying that he had cleared himself of fraud and objected internally. And they objected internally. So they objected to what had been put out, but obviously that didn't help. There were many papers we did not investigate for lack of time. A second committee, there was another committee also going on at the same time, which there was meant to be no connection between the two. Exactly the same outcome, which again, a very misleading response from the Birkbeck press office. That committee members, like mine, were extremely unhappy with this. Unless there is documentation that a PI has instructed the postdoc or student to fabricate data, the burden of proof of guilt cannot be achieved. So on the one hand, he's managed to slip by and not be held accountable, but both committees made it very clear that they didn't feel that he was blameless by any means. They just felt that more investigation was necessary. The only types of fraud we can see are image manipulation. Actually, so he's saying that the only types are image manipulation, but if that is what an entire theory or paper is based on, then it's not only the use of the same images with different legends. Financial fraud was also involved, since I presume these data either directly or indirectly were used to support promotions and grant applications. Then he wrote, in my last senior author position, means one is taking responsibility, sorry, in my mind, the last or the senior author position means that one is taking responsibility for the integrity of the work. Dr. Lachmann and Birkbeck apparently do not agree. So he was happy to have his name on everything, but when it came down to it, he claimed he had no idea what was going on, and none of these manipulations had anything to do with him. Another issue is that he also sits on the National Ethics Committee. So yeah, I'm assuming that's clear to you that there's an issue involved, that the same person who's giving the okay for these things may or may not be 100% clear of any wrongdoing. The second investigation, 2018, UCL declared that Lachmann committed recklessness and was insufficiently attentive to what his junior researchers used to do in his lab and his papers. However, Birkbeck, which is the place where they made the donations to and he was at the helm, claimed the matter does not relate to Professor David Lachmann's leadership at Birkbeck, which has been excellent for the past 15 years. Furthermore, there is no suggestion by UCL that Professor Lachmann had any knowledge of involvement in the image manipulation identified. So UCL, who weren't employing him anymore, I don't think, in 2018, were prepared to start distancing themselves from him, whereas Birkbeck stood staunchly behind him. If we look at the 2018 investigation, you've got, again, another 32 publications that is Claire Francis questioned. You've got a separate independent expert panel. Only 6 papers were screened. They proposed that they should widen the formal investigation. Decisions to retract on these 6 papers was made. However, obviously, that didn't necessarily happen. Only 1 or 2 of them, I think, were retracted. There was clear evidence of fabrication of figures. They also came to the conclusion that it was unlikely to be accidental. And they furthermore pointed out that in many cases, or at least some cases, it was fundamental to the conclusions. So you got a decision to retract 6 papers. Not all of that happened. There was clear evidence of fabrication, unlikely to be accidental. And yet, if we go back, we can see that Birkbeck is still saying everything's fine. This is just one example. Okay, you've got, I think she found to date 58 papers that have issues, but this is an example. You can see 2 images here that are flipped. Okay, you've got the same image, one slightly cropped, and the things that are labeled here, you can see apply in 2 papers that supposedly are totally different sets of data. So who's exactly to share the blame? Because you can see UCL originally backed him. Later on, they distanced themselves slightly. You've got this team of lawyers who are limiting what the committee can or can't say. So far, only of the 68 papers, only 14 were formally investigated. There's only been 6 retractions and 2 corrected. Here you've got a whole load of journals. Now they have access to all the information exactly the way I do or any of you do, and they've decided for whatever reasons not to retract or push for retractions. You've also got the 2 institutions where he worked, where at best one after it became almost embarrassing, kind of said that he was, his behavior needed, or his scientific behavior needed improving, but they didn't do anything more than that. So in terms of discussion, on the one hand, he hasn't necessarily been proven all the way. It's not like some of the other things that some of you have presented where we said there's no 2 ways about it. Here, his team of lawyers have somehow still managed to keep him above board, at least partially. So maybe we can look at it the other way around. Maybe this Claire Francis, who has nothing to lose really, her entire career or whatever it is based on bringing down or creating sensation. So who are we meant to believe? Should all science be open peer reviewed? If she's going to attack him in public, should she have to, come out and say who she is or what she has to gain from it? Then you've got the issue of money, finance. So also most of the papers or most of the fraud cases that most of you have displayed or given over, the people had money to be gained by what they were doing. Here, you've got someone who's spending, it would seem, huge amounts of resources in order to cover up the fraud rather than creating fraud as a source of income. So, you know, we seem to, money doesn't always seem to be the aim, but when you don't have it, then you're using the fraud to achieve it. If you already have it, then it seems that you use it in order to somehow, for whatever reasons, maintain the fraud. And then, is authorship ownership? Yes, he was written on all of them. It seems that even if he claims that he wasn't aware, there's still issues because there's too many of them and they weren't all linked. So he's the only common link between all these papers. But let's just say he wasn't. You know, if my name's going to be on something, am I the final stopgap? Do I have to be able to back up and support everything that's written? And if not, then you know, what should my name be on it at all? That's my 21 minutes.
Great. Thank you so much. Well, that was very interesting because this is not very conclusive. And I guess money and lawyers can change the outcome. This paper is open for discussion. Shoot, any thoughts, any comments? Do you know what he's doing now?
Yeah, he's still on the board for Bugbek. That's the thing. It's almost like they've got a direct open access to money from an institution that he decides where that money goes to. He's paid a massive salary by them.
Yeah, I mean, what I find really, this lasted for quite a few years. Students come and go, and the same practices are over the whole period. So that's not like I didn't know, maybe the students did it. There is only one common link.
Yeah, there's a common link, and not all of those students work together. There's a few different you know, collaborations between different people.
Interesting.
There's a question in the chat. There's a question in the chat.
Okay, in the chat. So the question is what the whistleblower has to gain. Since we don't know the name, we don't know.
So she may want to bring him down. It may be a personal feud.
Yeah, it might be a former co-worker, former student who. But on the other hand, just a minute, on the other hand, whistleblower is important sometimes because of authority and, you know, line of command and so on. You feel very uncomfortable to come forward. So there is tension there. I mean, should we accept anonymous complaints or no? Yeah, somebody wants to say something?
I just wanted to ask if the first papers were all came out at the same time, or were they like individually? Because at that time there was no link necessarily pointing towards what Lachmann.
There was a total of 68 papers, so they didn't all come out at the same time. No, in 2014-15, there was the start of an investigation for the first 30-something papers, and then she came forward. It came forward with a load of emails again that put pressure on them to look at another 30-something papers, but they didn't come out. You know, I don't think anyone puts out 30-something papers in one shot.
How many papers were actually?
Who initially?
Go ahead.
Who initially made the connection that this scientist was involved in all of the above mentioned?
It's an anonymous whistleblower. I think Claire Francis was definitely the second one. It wasn't clear. It wasn't made clear who the first one was. But I think she or the group is responsible for most of this. But it's not necessarily also the whistleblower isn't necessarily one person.
How many papers were actually retracted?
Only 6.
6. So, and that was with agreement with Lachmann, or the journals decided, or
he agreed after after the committee came forward. 2 are retracted and 6 were corrected.
Mm-hmm.
And then there were a few more that were meant to be retracted based on agreements, but they weren't. It never actually happened.
So I guess there is a scale for fraud. Sean is the one, and proper conduct is the other end, and you can find all kinds of levels. So this is somewhere in between, and therefore this is why it's so difficult to really decide. I mean, I guess a lot of his work was good.
Well, it's either good or people have too much to lose.
And he's so powerful and influential. But
I mean, you've got, there's 100 million pounds sterling there. It's
yeah.
And science needs money. So is there a way?
Yeah, there is a clear conflict of interest. So even the investigation itself is influenced by money.
Yeah.
Yeah.
Is there a way of us splitting the two? Because professors have to write their own grants, right?
Yeah. Well, I don't think it's healthy to have somebody so powerful. All right. Any other comments?
In the beginning, you showed us the Bar Ilan building. I think I missed how it is connected to this fraud. And what is the current status right now for this building? I mean, what's happening in there?
The building's fine. It's a beautiful conference center, and it can be booked, I'm assuming, through the university. It was donated. It was donated by the same trust fund that this Professor Lachmann is responsible for. It was money donated by his uncle. And I showed them in contrast, because that same trust fund donated over 20 million shekel, or over 5 million pounds sterling, to the same institution where he teaches and receives about over 1 million shekel a year as it's one of its head of staff. That was the connection, the money connection.
Got it. It's just that we don't see any activity inside that building ever, whenever we cross from there. So.
Actually, I went to a performance there last year. So they opened it when COVID kind of died out. It was a very nice event there. Every now and then there are some concerts and other events there. All right. Okay. Thank you very much, Avi. And our next speaker is David. David, are you here?
Which David?
David Lachmann. Seems like he's not here. So I don't know if there is any connection, but there is T in that last name. Okay, I see David Levy and David Gorelik, but I don't see a David Lachmann here. Okay, so let's move to our last speaker, which is Itamar. Itamar, are you here? Itamar is not here either. Okay. Either anybody here who is supposed to give a seminar next week or the week after and is willing to jump in.
Simon,
Sorry?
Simon, I am scheduled for today, so I would like to.
Oh, you are scheduled for today, so you are not on the Google Sheet.
I think I am, and it's David Lachmann is the topic of Avi lecture.
I don't know, I checked the, well, whatever, so maybe my mistake, but I checked it this morning. Go ahead.
Okay. I'm having trouble to share. Okay. Okay. So I would like today to tell you the story about the big hass over the stripy nanoparticles. And so the story begins in this publication that came out in Nature Materials in 2004. It was by Francesco Stalesi, a professor in the Swiss Federal Institution of Technology, ETH. He says his group coated gold nanoparticles, created gold nanoparticles coated with somewhat orderly striped domains of two different types of molecules. Because their unique ripple topology, they claims these particles can enter cells in a way that might be useful for drug delivery application and to trap toxic ions such as mercury. And this shows also a very promised environmental sensor. So I would like to present you the main players in this story, and you can see Francesco Stalesi on the left, and the other two guys that cricket him was mainly Raphael Levy from the University of Liverpool and Philip Moriarty from the University of Nottingham, both from England, and they both claim that Stalesi data don't prove the existence of stripes and is inconsistent and riddled with errors. So I would like to present my personal connection to this story. I got this story actually by mistake. I read first the papers, and then Raphael Levy came to give a talk in the Technion, and we are connected to their newsletter. And the first thing we did when I got the mail was to stalk him and search his name on Google, and then I saw on his, can you see my?
Yes, we can see the cursor.
He has a forum in his website, and he actually talked about it. And he began blogging about it in 2012, after he took years to get a correspondence for his paper that he and his group wrote, and it was actually published in a small journal. In it, he questions Stalesi's original report on striped nanoparticles, the same one I showed earlier from 2004, and especially on the scanning tunneling microscope data, STM, from this paper. So, oops. He originally sent it to the same journal that published the first paper, the Nature Communication, because he thought it's the logical steps, but they rejected him. So he referred to small, also a high impact factor journal, to raise his claim there. Even there, the paper took 7 referees during 3 years, which is a long time in terms of peer review. This is why he was pushed to the edge, and he started blogging about this topic. So those are the papers. Apparently they were published on the same day. I didn't know, but apparently it's mandatory to do. So Stalesi got the paper first, and then he published his response in the same time and concluded some new data. So the first article from 2004 mainly uses STM images as evidence for stripes. Stalesi's team coated nanoparticles with mixture of short and long molecules, and then imaged them, the particles sitting on a flat surface. They saw ripples on the particle surface that are interpreted by 9 to 10 Armstrong wide and striped domains in each compound. Stalesi says he didn't dream up the idea of different molecules separated into 2 colleagues and then striking to an interface. The community has long known that the mixed molecule could form patches or islands on flat surfaces, he said. And then the scientist was interested in whether the binary mixture of TIOL would arrange themselves in the curved surface of nanoparticles in a similar fashion. And this was his goal in the paper, seeing those stripes. When Levy looked in this paper, he was surprised too. But it was because he thought that the ripple was appearing in the STM and there were artifacts caused by improper use of the microscopes. In STM, the sharp tip is scanned across the surface, while a set of voltage difference maintained in between. The user doesn't want the tip to contact the surface, but to glide over it, tracing its features. One parameter research has to maintain the fixed distance between the tip and the surface is the gain. If the gain is set too low, the tip may not correct its position fast enough when approaching a bump on the surface and crash. If the gain is set too high, the stripe corrects it so rapidly that it bounces up and down the surface in an erratic fashion. Levy thought that he saw installated image that made the argument, did not make the argument, among other in his small, so that's why Levy raised the concern and wrote the small paper. And then Stelesi, in his response, published simultaneously as Levy paper, he fell back that he and his group had conferred the stripe over and over in peer review papers after this publication. And that Levy is ignoring this new data. He says, Stelesi says, science is a process and it will be fair to assume that later paper offer a better understanding of the system. So in this corresponding paper by Stelesi, he started collaboration with a new group, computational group, and running new simulation under the same condition that Stelesi claimed he made his experiment, and he saw the same results. He started collaborating with a group with Sharon Goltzer. And she says that it was the simplest explanation for this phenomena. Then Moriarty saw this paper, and he actually scanning probe microscope expert and began writing a guest post on the V-blogs after this small paper. He too was dismayed by the hard time Levy had getting his criticism into the journal. Publishing in the journal and Moriarty condensed should be a start of the debate, not the end of it. Moriarty said the simulation carried out by Glotzer and other high quality, but suggests a lot of assumption get under in running them, so they might not reflect reality. This actually reminds me something that Alicia Haas told me once, that an assumption is good as long you don't forget an assumption. And Shimon, I know you mentioned him in your talk last week, and I just wanted to share it too because
you can get in simulation anything you want. It really depends on what the assumptions and the parameters are. So if you want to get stripes, you can get stripes, sure.
Yeah. So Moriarty emailed Stelesi and asked for the raw data from his paper from 2012, a response paper, and Stelesi group sent it over and requested the image right away. Moriarty looked in the data and noticed something weird. Typically, an STM user will scan a large area, something like 100 nanometer by 100 nanometer surface. When the user sees a feature of interest such a nanoparticle, the researcher will zoom in on it and take a new scan over a smaller surface, something like 10 by 10 nanometers, to get a better view with high resolution. Rather than taking a small area scans, Stelesi and his team began zooming in on large area scans with a software program that interpolated between the data points and filled in pixels. Stelesi acknowledged that he plotted the data incorrectly. I wasn't aware, he says, I wasn't aware that the software and the microscope was adding points. But he claimed that this was only figures in paper, that the original scan, which have been recently reanalyzed, still shows ripples separated by 9 to 10 angstrom in this particle. So then he published a new set of papers in which stripes on his particle were once again identified, this time by microscopy experts such as Ryan of the University of Geneva in Switzerland and the Fater in the University of Louvain from Belgium, and Samoury, University of Strasbourg in France. These experts reached a image set of mixed towel particles from Stelles's lab, analyzed the data, and claimed found stripe.
So both these papers support the original claim of stripes.
Yeah.
Okay.
Another researcher from Italy actually suggested another method that he developed called power speckle density to analyze to analyze a computational technique that meant to remove any interpretation bias. He found periodic features that match the stripe of Stellesi as being seen. Okay. So Levin Moriarty says the new set of data is much better quality than the previous one, but they point out the image look nothing like pure image recorded in Stellesi's lab. The obvious ripples are gone, replaced with dots that Stellesi and co-workers connected to form stripes. Others agree that the existence of stripes still isn't clear. Stellesi and collaborator did a good PSD analysis, says Vladimir Sturko, a Georgian Institute of Technology, of the Georgia Institute of Technology, a material scientist with a background in scanning probe microscope. And he says, but stripes has not been proven. So Levin Moriarty have also written a new article, Critical Assessment of the Evidence of Striping Nanoparticles, which examines Stellesi's data old and new, STM and other measurements. They uploaded it to the archive and then later to PLOS ONE shortly after. And with this paper got more than 2,040 comments. It is currently the most discussed paper in the PubPeer forum, which also Avi mentioned earlier, I saw. Given all the work he has done in finding collaborators verified extended with stripes, Stellesi says he believes the critics are still trying to smear his reputation, he says. He says on Twitter, Levi has compared him with Hendrik Schön, and he finds this comparison unfair, given that he has never been found guilty of such misconduct. My critics are after me, not the science. On another blog post from a physics focus, Murtico responds on Stellesi claims of being bullied. Can I understand why Francesco might feel a victim? Yes. As a fellow scientist, I can entirely appreciate that a challenge of our research can feel like a direct criticism of ourselves. But also, at Richard is a research that is publicity funded should be debated in the open. He also tells on his forum that another reason he's taken the gloves off the fight reason that he has taken the gloves off in this fight is that the former student of Stellesi, Petra Durjnovic, came forward after Levi began blogging, indicating he had brought up concerns about the striped nanoparticle data with his advisor back in 2005. At the time, Durjnovic was a new grad student at MIT, tasked with studying whether the mixture of the molecule forms stripe on semiconductor nanoparticles rather than on gold nanoparticles that usually used in the lab. When he began to play around with the microscope, he says, he noticed that triple feature disappeared when he turned the gain down. Concerti went back to the basics, an image particle with only one type of molecule coated into them, as well as an uncoated one. Each time he saw that he could produce ripples in the image just by turning up the STM gain. He also claimed he went to Stellesi a number of times discussing his finding that they had some heated arguments. Eventually, the student was put on a new project. Stellesi says it is his policy not to discuss former students and would not comment on this story. But his student couldn't let things go. He felt unethically not to raise the issue further. So he discussed his concern with the department head in MIT, and eventually they put them into writing the university office of the vice president of research. A few months later, the official investigation of Stelesi launched at the MIT, and his student left Stelesi research group. MIT closed its review 3 years later, in 2008, finding Stelesi not guilty of academic misconduct. The university did, however, suggested that Stelesi should do additional work, sustained his 2004 findings. Stelesi tells that some magazine, C&EN, that he was already working on full statistical analysis of his data and addressed the suggestion that he published in 2004. For now, it seems Stelesi and his critics are in settlement. They say they don't see stripe. It's not only that I see stripes. The microscopists who have imaged my particles see stripes. The referees of the paper see stripes. He also says that he once offered to host Levy and Moriarty in his lab and run experiments together and to get to the bottom of the issue. Levy acknowledged the invitation, but says that he made under the condition that he would withdraw his 2012 small paper. Paul S. Wייס, pioneered in mixed molecule assembly on flat surfaces and editor of the ACS Nano, suggested the debate has to end eventually. The early data were inconclusive, he says. As a field, we are still going. New tools will be developed and applied to sort out what the arguments of the mixed molecules on the nanoparticles look like. Hopefully, we will discover a new phenomena along the way. So it's still open. We don't know the answer. And the question that I would like to raise after telling you this story is, can science self-repair itself? And did the scientific method work here? And did it keep the discussion going? And did it resolve it? Will it resolve it? And will it eventually end up with better understanding and better science? And another thing I would like to raise are, what are the motives of them? So thank you.
Thank you, Leon. So let me go first. I don't see really any issue of ethics here. I see here maybe bad science. So anybody who worked with STM, and I did quite a bit of work in early years, when you have too much gain, you get overshoot, you get this type of data you showed. And you as an STM practitioner, you have to be aware of this. So if indeed there are things, simple artifacts, I think that should have been checked and discovered. If I understand correctly, what Paul Wייס is saying is there are no good enough tools right now to really look if we see different arrangements of those ligands. I'm not sure about that. I mean, you can get sub-angstrom resolution with STM nowadays. So I'm actually surprised that this is not resolved. Any other comments? Anybody thinks there is some fraudulent science here? There's an argument.
I think it's pretty close. It's not clearly a misconduct, but it's looking away when you get criticizing. So it is.
Yeah. Well, I mean, you get defensive, right? And you want to believe that what you've done is correct, but pushing the student away and then pushing the reviews away, it's being very defensive. And I don't think he has strong evidence for stripes at all. So as a scientist, you should be open, and you should be open to the fact that you might have been wrong, rather than be very defensive and protective of your paper. especially if you might, if later, years later, you are proven wrong, you will not come nicely out of this, right?
He did write like the revised papers when people said it was, when you say interpolated images or whatever, that the images weren't so, and he did put out new articles, but I think the original article also, like, he should have been quick to correct it and make, or note the correction, or even retract it himself. That I think was like also just a really hard head or kind of thing.
Yeah. But you have not shown us figures from the new papers where they kind of did more work. You said
where he corrected the images.
In this case, they did not have striped. They had some non-uniform images.
It's much more homogeneous, so as the dots and crossing each other, not stripes.
Yeah, it would have been helpful if you could clip a figure or two from those papers.
I'm not an STM guy, so it was hard for me to conclude for myself.
No, I'm just saying that putting side by side the original image from the original paper versus the image from a much later paper that was less conclusive, that would be interesting to see. Anything else? Great. So thank you very much, Leon, again. So I'm a little bit confused with the list of names I have for today. Is there anybody else who is supposed to speak today that I missed? No. Okay, great. So we are going to meet again in a week from now. It will be virtual only. I want to emphasize again, I send it in the chat, I'll send the email as well. In order to get a grade in this class, you have to send me your PowerPoint. You have to send me your 2 pages PDF, and you have to show up. So we are taking attendance in this class, and today, for some reason, we have much fewer people than usual. So just, to your attention. Anything else that anybody wants to say? Not have a great evening. Thank you all. Bye, Latov.
Bye. Thank you very much.
Bye. Thank you.